So section 2.7, it's about optimization, and I'll divide this section into two parts. In part one, we'll be talking about relative maximum and minimum. And in part two, we'll be talking about global or absolute minimum and maximum. Okay, so the first thing first. So we'll be talking about part one, relative, or sometimes called local minimum and local maximum. Okay, or you can say local extrema. Extrema means it represents either minimum or maximum. Okay. So minimum and maximum, that's very useful concept. As we discussed earlier, in our real life situation, there are so many instances where we need to figure out what is the maximum value and what is the minimum value. How, for example, if you have a company and you want to find what is the maximum profit for the company. Suppose you have a function, profit function given for a company, then you can find what is your maximum profit, at what quantity level you can maximize your profit. And suppose you are given a cost function, at what point you can minimize your cost. So that kind of things is really important in our day-to-day life. So that's what we're going to learn today. So basically, in the first part, we will focus our attention on the mathematical process of finding maxima and minima. Okay, and then the real world application. There is another section, we'll talk about that in our next week class. Those questions particularly taken from business and economics, and then we'll use the concept that we learned today to minimize and maximize the given function. Okay, that's what we will be doing next week. But today we learn the process, we learn the method, how to minimize and how to maximize the given function. Okay, so today, as I said earlier, in this part, we'll focus our attention on relative, sometimes called local extrema. What this local extrema means is that, look at this graph. As you can see here in this graph, this is your maximum point. This is your minimum point. This is your another maximum point. And this one is the end point. Okay. This one is called relative maximum, and this is another relative maximum, or sometimes called local maximum at x equals, this is x1 and x3. So at these points we have local or relative maximum, and local minimum at x equals x2 here, and there is the endpoint as well. Now the question is, out of these two maximum, let's say, okay, there are two maximum, and out of these two maximum, the true maximum, the real maximum is this one. If we look at the graph globally, okay, when we look at the neighborhood, certain neighborhood, that's why we call it local. In this locality, yes, we know that this is the maximum value. In this locality, this is the maximum value. But when we look at the whole graph, the graph as a whole, then this is the true maximum. Therefore, we call it absolute maximum, or sometimes called global maximum, is x equals x1. Okay, again, the global maximum and minimum, we'll talk about that later. So now let's focus our attention on local maximum and local minimum only. So I think if you are given the graph, I think you can tell where the maximum, local minimum, and local maximum occurs just by looking at it. Let us look at the relationship between the derivative and local minimum and maximum and increasing and decreasing function and all this stuff, okay? If I draw a tangent line there, you see that the tangent line is horizontal. That means the derivative is 0. If I draw a tangent line at the minimum point, again the derivative is 0 here. Okay, the derivative is 0 at this point. If I look at this point right here, which is another local maximum, at this point we have derivative is undefined. Now, this graph is increasing, going up. That means the derivative is positive. This graph here on that side, on that interval, derivative is negative because it's going down. We discussed that already in our last class, that when the graph is increasing, derivative is positive. When the graph is decreasing, that means in the language of calculus, we call it derivative is negative. And here again, this decreasing means, I mean, here on this part, let me write this here. So at this point, we already saw that derivative is 0. But this side, derivative is positive because it's increasing. Derivative is positive. And here, the derivative is negative again because it's decreasing. Now, a couple of things, very important observation, guys. When the derivative is 0 or undefined, we used to call it, we call it critical numbers, critical points. Remember from our last class. So this is one critical point. This is another critical point, another critical point, okay? So the minimum or maximum occurs at those critical points. In other words, critical points are the candidate for maxima and minima. Keep that in mind. Let me repeat that again. Critical points are the candidates for local minimum and maximum, or relative minimum and maximum. If the graph is positive, I mean, if the derivative is positive on the left-hand side, on this side, left-hand side, and the derivative is negative on the right-hand side, so at that point we'll have maximum. If the derivative is negative, on the left but positive on the right, then we'll have minimum value. So keep that in mind. Let us look at this quickly. This side, your derivative is, because the graph is increasing, derivative is positive. This side, derivative is negative. So we have maximum there. Okay. Here, the graph is decreasing, derivative is negative. And here, graph is increasing, derivative is positive. So we have minimum there. Just keep that in mind. That's how we test. Okay. Just by looking at the graph, I would like you to think and let me know where the graph has relative extrema. Remember, extrema means minimum and maximum, both. So I want you to tell me what is the local maximum at x equals, local minimum at x equals. So you already know that at x1 we have minimum, at x2 we have maximum, at x3 we have minimum. So local maximum at x equals x2, local minimum at x equals x1 and x3. Okay. And notice that this one is the critical number, this is another critical number, this is another critical number. So the maximum or minimum always occurs at critical points. And I think you already know what is the critical point, critical number, critical value is. We discussed that in our last class actually. But if you need to review, then here is the definition. You can have a look quickly. Now, if the graph is given, then you can tell whether it's minimum or maximum just by looking at the graph, right? Not a big deal. But you know, life is not that always easy, right? Sometimes instead of graph, they give us the function like this. And how do we do that? Well, one method is to draw the graph. But drawing graph for function, easy function, okay, I think it's not that hard if you are given the easy function. But if you are given a ugly functions like f of x equals, x is square root x plus x3 over 2 minus, ln x, something like that, then drawing graph of those functions is not fun, right? It's not easy. So in that case, how do we find the maxima and minimum values? Well, we can find it using, that's the power of calculus, okay? Even without drawing the graph, we can find where the maximum occurs and where the minimum occurs and what is that maximum value and minimum value. We can find that. So we're going to use the power of calculus to do that. And that's what we're going to learn now. Let's look at example 1. Let me just copy the question. Given the function f of x equals 2x cubed minus 3x squared minus 12x plus 12. First, you need to find the derivative, which is 6x squared minus 6x minus 12. Now, we're going to follow those 4-step method here. Step 1, find the critical number. Step 2, put the critical number on the number line. Step 3, choose the testing point. Step 4, analyze the sign. It's exactly the same thing. These 3 steps, step 1 to 3, we have already done a couple of times in the previous section, in the previous topic, okay, in our last class. It's exactly same thing. Guys, I want you to try this on your own, all right? You already know how to do those 3 steps. So the first thing, we need to find the critical number. And here, part A is find the critical number. Remember, in this question, we have to find critical number interval where the function is increasing and decreasing, which is step 2 and 3, and find the relative extrema, which is step 4. So A, step 1. So for critical number, we know that f prime of x equal to 0 or undefined. Derivative is undefined. So there is no such number. So this one is 6x squared minus 6x minus 12 equal to 0. And if you factorize, x squared minus x minus 2 equal to 0. If you factorize, you're going to get x minus 2 and x plus 1 equal to 0. I trust that everybody know how to factorize it. And so you have x equals 2 and negative 1. Step 1 is done. Step 2. So we need to find where the function is increasing and where it is decreasing. So for that, you need to draw a number line and plot those points. And choose the testing points. So 1 point from each interval. Remember, the number line has been divided into 3 parts. We have 3 interval, 3 parts by using this critical points. So you choose any number between negative infinity and negative 1. choose the number that makes your life easy, which is I think you may want to choose -2 maybe. And on the interval -1 and 2, you may want to choose 0 to make your life easy. But remember, you are allowed to choose any number in between these two values, okay? For example, for -infinity and -1, you can choose -3427.3 if you like, but I suggest that make your life easy. So the second interval, we choose a nice easy number, which is 0. In the third interval, let me choose 3. Now let us test this. Let me just copy the function, which is 6x square minus 6x minus 12. That is the derivative. And we need to test those points there. So when I plug in -2 there, I'm going to get -2 square minus 6 times -2 minus 12. And you know that if you simplify it, you're going to get positive number. So this guy is positive. So the graph is increasing there. Now let us find when x is 0, that's going to give me, and this is negative clearly. Okay, if you simplify, you're going to get negative there. And then when you test with 3, you're going to get, this is again positive clearly. So step 2 and 3, by the way. So this is our part B to find increasing and decreasing interval. Okay, so what we notice is that the graph is increasing on the interval -infinity to -1 and then 2 to infinity. So in this 2 interval, the graph is increasing and it is decreasing on the interval -1 and 2. Part C, we need to find the local or relative minimum and maximum values, okay? Now recall when we analyze the sine, the graph is increasing on this interval and then at -1, it starts decreasing because that is the critical point and where the graph changes its direction. Clearly, this should be maximum, right? It's going up and then going down. If something goes up first and then goes down, you can see that that is the maximum point. Okay, so to find relative or local minimum maximum, so we analyze the sine. After analyzing the sine, we notice that the maximum at this point. So we notice that maximum at x equals -1. And now at 2, what happens? Okay, this is another candidate for maxima and minima. What happens? It's going down first on the left side, and then on the right side, it's going up. So clearly, this is minimum, right? So minimum at x equals 2. Now we need to find the maximum and minimum value as well. So maximum value, how do we find that? Maximum value means the y value. Y value means the f of x value. So the f of x means when x is -1, you plug in this in the original function. So your original function will be 2 times x cubed, which means -1 cubed, minus 3x squared. X means -1 squared, minus 12x means -1 plus 12, which gives me, you can calculate that yourself. And the minimum value will be y equals f of when x is 2. That's going to give me 2 cubed minus 3 square minus 12 times 2 plus 12. And then if you calculate it, you're going to get 19 there and -8 there. So what we found is that if you want to write this as a coordinate, you can write this when x is -1, y is 19, when x is 2, y is -8. So that's this is our maximum value and this is our minimum value, minimum point. Okay, so that's it. Okay, all right, guys, this is the process to find minimum and maximum. We're gonna use those 4-step methods, and we find the minimum and maximum. And by the way, this method of testing minimum and maximum is called first derivative test. There is second derivative test. Okay, there is another test as well. There is another method to find local minimum and maximum. We'll learn that later. So right now we are using the first derivative test. And there is another method called second derivative test. We'll do that later. Now, if you understand how to do this, then probably you will be able to solve pretty much everything. I mean, every other examples given here. But we'll try one more question just for fun. So example 2, let's say. Example 2, the function is given f of x equals x squared minus 2x plus 1 over x minus 3. Now, I trust that you know how to find the derivative. If you find the derivative of this using the quotient rule, okay, this is your u over v. Using the quotient rule, you're going to get uv minus uv over v squared, prime. And okay, guys, try this by yourself. All right, so what we found is that the derivative is this. Let me just copy the derivative here on this side. So our derivative for this function is going to be x minus 5 and x plus 1 divided by x minus 3 squared using the quotient rule. That's what we got. Now, step 1, find the critical number. So this is part A. Step 1, find the critical number. So for critical number, we know that derivative equal to 0 or derivative is undefined. So derivative 0 means, as we already know from our previous class, that we equal the numerator 0. So that means x minus 5, x plus 1 equal to 0. And to make this function undefined, then x minus 3 squared, the bottom part is 0. If the bottom part is 0, the function will be undefined. So from this one, I got x equals 5 and -1. And from this side, I'm getting x equals 3. Now, the question is, what is the critical numbers? So critical numbers are x equals 5 and -1, because x equals 3 is not in the domain. This is not in the domain. So critical number are 5 and -1. That means the candidate for maxima and minima is only x, either maxima and minima will occur at 5 and -1, not at 3. However, the goal here is to find where the function is increasing and decreasing. So for that reason, what we do is in step 2 and 3, when we draw the number line, we include -1, 3, and 5. We include that 3 as well. Sometimes, even though it is not critical number, even though it cannot be minimum and maximum at x equals 3, but sometimes the graph may change its direction. So for that reason, we just put that 3 here as well and test. Now your testing point, x equals, in the first interval, you may want to choose -2 maybe. In the second interval 0, third interval 4, and fourth interval 6. These are the testing point. Let me just copy the function, the derivative function here, which is, my derivative is x minus 5, x plus 1 over x minus 3 squared. If I plug in the value, -2 there, so this guy will be -2 minus 5 and -2 plus 1 over -2 minus 3 squared. Notice that the bottom part is always positive, because always non-negative because of the square. Okay, so the only sign that you need to test is on the top part. So if you test the top part sign, here we are not interested in the value, we just interested in the sign, whether it's positive or negative. That's what we are looking for. So -2 and -5 is -7. -2 plus 1 is -1. So the negative times negative will be positive. So this guy will be positive. And let's try plugging in 0. When I put 0 there, I'm going to get 0. You can do this in your head. Okay, you don't have to write all of these things. So this is clearly negative. So this is negative. Now let's try at f prime of 4. When I plug in 4 there, what I get here is that, okay, you can do this in your head. You don't have to write all of these things. If I plug in 4 there, 4 minus 5, which is negative, and 4 plus 1, which is positive. So negative times positive will be negative. So this is negative again. Now f prime of 6. If I plug in 6 there, 6 minus 5 is positive, 6 plus 1 is positive, so positive times positive is positive. So this guy is positive. So we already know that the function is increasing on the interval, f of x increasing on the interval -infinity to -1 and 5 and infinity, and decreasing on the interval -1 to 3. Some people write this, it's decreasing all the way from -1 to 5. People sometimes write this one in the exam, which is actually wrong, because then you are including 3 as well, but 3 is not in the domain, so you cannot include that point. So you must write -1 to 3 and 3 to 5. That's where the function is decreasing. This part is done. And the last part, we need to find out where the function has maxima and minima value. Okay, part C for maxima and minimum values. notice you just analyze the sign. Now let us analyze the sign to figure out where the local maximum and minimum occurs. As we know from this graph, you can see the graph is going up first and then going down. So that means it must be maximum at that point. We know that when the graph goes up and then down, we'll have a maximum. Here, the graph goes down on the left hand side, but it also down on the right hand side, no sign change. So at this point, there is no minimum and no maximum. No minimum, no maximum. It is because you know that this is actually not in the domain. No minimum maximum at this point. Now here the graph is going down and then going up. So when the graph goes down and then up, we'll have minimum value. So at this point we have minimum. So we notice that maximum at x equals -1. So we notice that maximum at x equals -1, minimum at x equals 5. And we need to find the maximum value as well. So maximum value means y value. Maximum value, which is y equals f of -1. So let us plug in this value in the original function, and the original function is -1 square minus 2 times -1 plus 1 divided by -1 minus 3. So if you simplify, you're gonna get, I believe, 0. And let me add one word here, local maximum, okay? Relative, I'll write relative or local, R maximum. So R means relative minimum value, y equals f of 5. So when I plug in 5 there, I'm gonna get 5 squared minus 2 times 5 plus 1 divided by 5 minus 3, and that's gonna give me 8. So the maximum value is 0 and minimum value is 8. Wait a minute. Does that make sense? Maximum is 0 and minimum is 8. Did we do something wrong? Is it possible? Minimum is way bigger than maximum. Is that possible?
No.
Well, for yeah, it sounds counterintuitive, right? So it sounds, because we tend to think that maximum of a function should be greater than minimum value, but for local minimum and local maximum, it is perfectly fine. Let me show you one simple example. We will be drawing the graph of this function and we see what is going on, but I just want to give you one simple example, okay? Let's say this is your function. This is your maximum. This is your minimum. This is also your minimum. If you compare this maximum with this minimum, then clearly this minimum is bigger, right? This minimum is even bigger, sometimes possible. But for this graph, let's see what happens, what is going on here. I want to draw the graph of this function. So the graph is, okay, the function is our origin. Let me just copy the function here, okay? Our function is actually x squared minus 2x plus 1 over x minus 3. So this is the function. I'm gonna, pull up my graphing paper, and my graphing paper is actually the GeoGebra. Let me just pull up GeoGebra, okay? So let me draw the graph of the function. Our function given, the original function given to us was x squared minus 2x plus 1 divided by x minus 3, right? That was the graph. And what is going on here? As you can see, clearly this point 1 and 0 right there, this is your maximum, because by definition the graph is increasing on the left hand side and decreasing on the right hand side. So at x equals -1, the y value is 0, which is the maximum. It is the top of the mountain. And this one, when x is 5, your y is 8, that is the minimum by definition, right? It is the bottom of the valley. So it is okay to have maximum is smaller than minimum in case of relative or local minimum and maximum situations. All right, so example 3, I leave it to you. I trust you guys, you know how to do it. If there is any issue or if you need help, then I will post the detailed solution in my lecture note later in Canvas, okay? Now, let's look at one more example, one simple applications of this concept in business and economics. So example 4. Guys, I want you to try this on your own, okay? First, let us look at what is going, what is the questions is all about, okay? We need to find the maximum weekly profit and the price a company should charge to realize maximum profit. If the cost function is given, CFQ equals 100 plus 10 cube, and price P is given 50 minus 2 cube. So the solution here is, first of all, we need to maximize the profit, means we need to find the profit functions, okay? To find the profit function, we need the revenue function. So first, revenue. Revenue means price times quantity, we know that. Price is already given, which is 50 minus 2 cube, and quantity is q. That's going to give me 50 cube minus 2q square. That's our revenue. So the profit is profit P of q is revenue minus cost. Revenue minus cost. So revenue is, we just found, which is 50q minus 2q square, minus cost is 100 minus 10q. So that's going to give me 50, okay, negative 2q square. 50 minus 10 is plus 40q and minus 100. Okay, that's what we got our profit function. So profit P of q, notice that we generally use the lowercase p to represent the price and the uppercase p to represent the profit, okay? So P of q, let me just copy that function. Profit function is negative q is negative 2q square plus 40q minus 100. Now, again, using those 4-step method, I would like you to complete this by yourself. And once, take 5 minutes or so, and once you complete, then we will discuss. So to find the maximum profit, what you need to do is, by following the same steps as we did earlier, you find the derivative, which gives you negative 4q plus 40. And for critical point, you have derivative equal to 0. That gives me negative 4q plus 40 equal to 0. That gives me q equal to 10. Now the question is, we know that q equal to 10, either it will be maximum or minimum, we don't know yet. So what we need to do is we need to do the sine test, analyze the sine. So you draw a number line and 10 is there, and this, your domain is 0 because we are talking about quantity here. You cannot go to negative infinitive. It's just up to 0 to infinitive. Now testing point, your q equals maybe the easy number would be 1, and another number could be 11. Okay, so then p prime of q, let me just copy that function, derivative function, which is 4 cube plus 40. So p prime of 1 is going to be negative 4 times 1 plus 40, which is definitely positive. And then p prime of 11, which means negative 4 times 11 plus 40, which is definitely negative. So this side is positive, this side is negative. And now this, according to the sign analysis, we know that this is going up on the left from 10, the graph is going up, and then graph is going down, so therefore we have maximum. Okay, so we prove that this is maximum. So maximum at q equals 10, and maximum profit is, and maximum profit p of 10 is going to be, you just plug in this value in the original function. So the original function is negative 2 q square, means 10 square, and plus 40 times 10 and minus 100, that's gonna give you $100. Okay, so as we have seen earlier, to test whether the critical point is minimum or maximum, what we did is we used the first derivative test. For all the examples that we have done so far, we found the critical point. And once we find the critical point, then we use the first derivative test. What it means is we draw the number line and we plot the critical point, and we have intervals on the number line, and we test and we analyze the sign, and then we figure out whether that critical point is actually a maximum or minimum. So this method that we did is called, this method right here is called the first derivative test. But sometimes, the second derivative test is a lot easier than this. Okay, there is another method called second derivative test, and that method will be really handy in many situations. How do we use that? All right, so please focus your attention here. Look at this graph. As you can see here in this graph, this is the inflection point, okay, IP. So the graph is concave up on the interval negative infinity to 0, and then concave down on the interval 0 to infinity. Okay, there are two intervals. One interval is concave up this side, and another interval is concave down this side. Now tell me, if the graph is concave up on that interval, whether we have relative minimum or relative maximum occurs. Clearly relative minimum, because as you can see, the graph has this concave down, means it's this kind of shape of the graph. So on this part, on this interval, we always have minimum value. When the graph is concave down, on that concave down interval, we have the maximum value. So now, concave up means the second derivative is positive. So when the second derivative is positive, we have minimum value. When the second derivative is negative, we have the maximum value. Please keep this in mind. These are the two very important concepts. Okay, you will use it in this course, and you'll use any other math calculus course that you'll be taking in the future. This is a very important concept. Please remember, second derivative positive means concave up. So when the graph is concave up, that's the interval where the minimum actually lies. Concave down means the second derivative is negative, and that's where the maximum point lies in the graph. So with this idea, let us let us solve one problem. Example 5, part A. Okay, so we are given the function negative 2x cubed plus 3x squared plus 72x. Now find the derivative. Because we are going to use the second derivative test, so you need to find the first derivative and second derivative. Okay, so the first derivative is going to be negative 6x squared plus 6x plus 72, and your second derivative is going to be negative 12x plus 6. All right, so now let us find the critical number. It's the same method, guys, okay, to find the, because we need to find the critical number because they are the candidate for maxima and minima. So for critical number, your derivative equal to 0, which gives me negative 6x squared plus 6x plus 72 equal to 0. And if you solve it, let me know what you get. So if you solve it, I think it will be, okay, let me do it here. This gives me negative x squared plus x plus 12 equal to 0, or you can write this negative 6 common. You can write x squared minus x minus 12 equal to 0. So that's going to give me x minus 4 and x plus 3 equal to 0. So that gives me x equals 4 and 3 minus 3. All right, so we got this 2 point. Now these are the candidates. So critical points are x equals 4 and negative 3. We know that. So they are the candidate for maxima and minima. Now we need to test, okay? To test for maxima or minimum value, what we did earlier is that we used the first derivative test, which means we have to draw the number line and then plot those critical points, and we have interval and test the points. Now, to test for maxima or minima, let us use the second derivative test, okay? We use second derivative test because we can use first derivative test as well if we like, but we want to learn the second derivative test here, okay? So second derivative test means, let me just copy the second derivative. This is my second derivative, and let me copy the critical points. So here what you do is you plug in those critical points here. So test the critical point here. Test the critical points. That means second derivative when x is 4. Here is the critical number. X is 4 and x is negative 3. So when x is 4, that's going to be negative 12, 4 plus 6. Clearly, this is negative. So that means x must, 4 must be, what does that mean? Its second derivative negative means concave down. Okay, concave down. It's like if you want to use this negative means, negative concave down. So this guy has a negative mood, you can see, not happy, concave down. So if it is concave down, that means clearly it will have a maximum value. So we have maximum. And the second derivative, when -3, that gives me -12 times -3 plus 6, which is positive. Positive means concave up. Concave up means, your mood is up, so you are up. That means positive, you are up. Okay, you are happy. So that's minimum, because you see we have this kind minimum. So, and then we know that maximum at x equals 4, and maximum value you can calculate by plugging in the original function. So maximum value y equals f of 4, plugging in the original one, and minimum at x equals -3. So minimum value will be y equals f of -3 equals, okay, let us plug in this value and see what happens. So when I have x equals 4, I'm going to get -412 times 4. I'm plugging in this value. I'm plugging in this value in the original functions, okay? 12 times 4, -12 times 4, and plus 4 cube, and plus 3 times 4 square, plus 72 times 4 equals, you can calculate that by yourself. And when I plug in -3, I'm gonna get, yeah, I leave it to you. So that's -12, -3 cube, plus 3 times -3 square, plus 72 times -3. And so my calculator tells me that this value is 208 and this value is -135. So what I got here is that maximum at point, if I write this as a coordinate system, then I'm gonna get 4 and 208, and minimum at -3 and -135. That's it. This is called second derivative test. Okay, so generally, if the function is a rational function and you have, the second derivative is difficult, then the first derivative would be your best choice. But if finding second derivative is also easy, then your first choice may be the second derivative test. Okay, but one caveat though, one thing that you need to know, what we discuss is that when second derivative is negative, it means concave down, which means maximum. Second derivative is positive, concave up, which means minimum. We know that. But sometimes if you get second derivative equal to 0, then this method fails. Okay, in this case, the method fails. So this is a drawback. So when the second derivative is 0, then this second derivative test is not going to help you. You must use the first derivative test. By the way, first derivative test can be used all the time. Okay, there is no situation where you cannot use the first derivative test. But second derivative test sometimes doesn't work. Just keep that in mind. And that's it. Okay, clearly in this answer here, so the original function is not -12, it's 2. Actually, I plug in 2 there in my calculator, but somehow I wrote -12 to check how many of you are paying attention. Okay, yes, there are a few people who caught me. Thank you. So that is -2, and then all the other will be 3, 4 square plus 72, and I think that's correct now. Okay. So our final answer is maximum at 4, and the maximum value is 208, and minimum at x equals -3, and the minimum value is -135. Okay. So I trust that you can handle part B very similar. Like I said, you can use first derivative test or second derivative test, doesn't matter. But most of the time, the second derivative test is a lot easier. It makes your life easy. But the drawback is that sometimes this method fails. Okay, so yeah, so in the future, sometimes we use first derivative, sometimes we use second derivative, depending on the situation, depending on the type of functions we are given. So we will learn that down the road. All right, guys, in this section, part 1, this is what we are supposed to do. And in part 2, the second part is we'll be talking about global maxima and minima in our next class.